Okay, so I want to start out with the definition of E. Um, I think that you've probably seen the formula P times e to the RT, and that you've also seen P times 1 plus R over N to the NT. So this is, you take the annual rate, you divide by the number of compounding periods, so that's the rate per compounding period. And then the total number of compounding periods is the number of compounding periods per year times the number of years. And then you've also, as I've said, I believe, seen this one. I thought that color was going to work, but it's not. So hold on. Okay, so I'm just going to point out, first of all, that the P's are the same and the T's are the same also. So this is to the RT. Because in both cases, like I could to the T, e to the R, to the T, because if you have a power, something to a power, and then all of that to a power, then you can multiply the powers. So I'm just kind of undoing that multiplication. So I want to look at the inner pieces of these only and skip the P's and the T's for now, just to save writing things down. Okay, so this one is within compounding periods per year. This one is continuously compounding. So basically, the way you get from compounding n times per year to compounding continuously is let this number of times per year go to infinity. So this is a limit. So if I let the limit of this, if I let, not zero, if I let n go to infinity, then this goes to e to the r. So this wasn't some like magic thing that happened where E did this. They wanted to know what this number would be. And when they found it, it was irrational. So they named it. So the limit as n goes to infinity of 1 plus 1 over n to the n is just E. So that's what it's named to do. Pi was named to be the proportion of circumference to diameter. E was named to be this limit. Okay, so now I want to consider e to the x. So e to the x is the limit as n goes to infinity of 1 plus x over n to the n. Okay, so n is the thing that's varying and going off to infinity in this case. But then I want to look at the derivative with respect to x. So now I'm going to look at the limit as h goes to 0 of e to the x. Oh, actually, no, I don't want to do that. I don't want to do this by definition. Okay, so I want to take the derivative of this using rules that we've already learned. So I want to take the limit as n goes to infinity of the derivative of this. So remember that n is going to infinity, but I'm taking the derivative with respect to x. So because I'm doing that, these n's act like fixed values. So I've got something to the n, so the chain rule says bring the n down. And then 1 plus x over n to the n minus 1 times the derivative of the inside, which is just 1 over n, because this is x times 1 over n, 1 over n. So these cancel. So I want to point out that this is the limit as n goes to infinity of 1 plus x over n to the n times 1 plus x over n to the minus 1, all in parentheses. If this limit exists, which it does, you can sketch e to the x and see that there ought to be a derivative anyway, then I can split this, because remember that the limit of the product is the product of the limits. So that's the limit as n goes to infinity of 1 plus x over n to the n times the limit as n goes to infinity of 1 plus x over n to the negative 1. Now, because I don't have an n up here anymore, I can consider kind of what's on the inside. This is 1 over, well, let me just, so this first part, limit n goes to infinity, 1 plus x over n to the n, was the definition of e to the x. And then this is times the limit as n goes to infinity. This is 1 over 1 plus x over n. So as n goes to infinity, x over n goes to 0. Because x is not the thing that's varying here, n is. So that x, imagine it's 3. Whatever x is, n eventually gets way bigger than it because n is going to infinity. So this thing is going to 0. So this whole thing is going to 1. So this is the cool thing, which is the derivative of e to the x is e to the x. And due to the chain rule, e to a function is e to that function, because first you leave the chocolate alone, and then just the derivative of the exponent itself. So we have this. The derivative of e to a function is e to the function. So you copy down exactly what you had, and then you multiply by the derivative of that power. Okay, so for this first one, y prime is, copy down what you see exactly, and then the derivative of the power. So I'd probably write it like this. The next one, write down exactly what you see, and then multiply by the derivative of the exponent, so minus 0.1. Negative 4 times negative 0.1 is 0.4. And then on the last one, we write down exactly what we see. And then the derivative of the power is 3 times 4 is 12, x to the drop 1, so squared. So negative 60 x squared e to the 4x cubed. Okay, so this one I have a product. So u is x cubed, v is e to the 4x squared plus x, u prime is 3x squared, v prime is, copy down what you see, and then take the derivative of the exponent, so 8x plus 1. So u prime v plus v prime u equals 3x squared times e to the 4x squared plus x plus e to the 4x squared plus x times 8x plus 1 times x cubed equals, so I have an e to the 4x squared plus x in both cases, so I'm going to factor it out. Three x squared plus 8x plus 1 times x cubed so equals e to the 4x squared plus x times 3x squared plus 8x to the 4th plus x cubed. So you could pull out an x squared if you wanted to. Okay, quotient rule. U is e to the x, v 2x plus 1, u prime, also e to the x, v prime 2, u prime v minus v prime u over v squared is e to the x times 2x plus 1 minus 2 e to the x over 2x plus 1 squared equals, factor out the e to the x, and you have 2x plus 1 minus 2 . Okay, so I think I saw this one was the last before we talking about other bases besides e. So recall from sometime in your past life that e to the natural log of a number is that number. These two are inverses. So if I have a to the x, I can rewrite that e to the natural log a to the x equals e to the natural log a times x. So if I want to differentiate this, then I can differentiate this. So I write down what I see, and then I multiply by the derivative of this power. But the derivative of the power, this is a number times x, so this is linear, so it's just that number. And you could write this as x to the 1 and bring it down and 1 minus 1 if it's especially bothersome to you that this is the slope of that line. So now I'm going to put this back, this e to the natural log a. So this is natural log a times e to the natural log a to the x is natural log a times a to the x. So that's the derivative if your base is something other than e. And you can do this when the base is e, it's just that natural log e is 1. So there's that rule. And then we can use the chain rule just as we could with e. Okay, so just like before, I'm going to start out writing down y prime is, I'm going to write down what I see. But now I have just two things. I have one that I need to do a natural log 8 because the base is different from e, and then the derivative of the power. In this one, I have a product. So u prime, 2 times 10 is 20, t, drop a degree, v prime is, write down what you see, multiply by the natural log of the base, and the derivative of the top. U prime v plus v prime u equals 20t times 2 to the minus t plus, well, minus 2 to the minus t times natural log 2 times 10t squared. I should start that line over, that looks bad. Okay, u prime v, now I did it again, plus negative 2 to the negative t, natural log 2, 10t squared, equals, I can factor out the 2 to the negative t, you get 20t minus natural log 2 times 10t squared. You could factor out a 10t if you wanted. There are several things you could do to clean this at this point, but you don't have to at this stage. You just have to be able to recognize what it's equal to if it comes to it. Okay, so so the first thing that I'll do, I guess, is to put this into the calculator. So, well, 100,000 divided by. Be sure and put the parentheses there, or it'll just divide by the 1 and then add the other thing. 1 plus 100 e to the negative 0.3 x. And then window, you're going to do negative 10 to 50 and then 50, oops, 50 to 100,000. This is what's sometimes called an S-curve in some of the sciences. It's a logistic function. Basically, it's when something starts out at an exponential growth, but then it kind of plateaus, which happens in nature because, sorry, it's getting very late. It happens in nature because you run out of space or run out of resources and so forth. But it happens in this case on sales as well. So we want to find and interpret the rate of change after 4 years. So I'm going to take this. Now there are two things you could do. You could write this as 100,000 times and then write the denominator to the negative 1. Or we can treat it like a quotient. So if you treat it like a quotient, so u prime is 0, v prime is, write down what you see, and then we need the derivative of that value. So negative 0.3 times 100 is negative 30. U prime v minus v prime u over v squared is, u prime is 0, so that part I can just skip. 0 minus. V prime is negative 30, so plus 30 e to the negative 0.3x times u, 100,000, over v squared, so equals 3 million. Okay, so we wanted to plug in 4. So negative 0.3x is negative 1.2. Some concern that I'm going to do something wrong with this one. Okay, hopefully that was entered correctly there. So 933. So because it's positive, and remember that this is this is sales that can be approximated in the first few years, where X is the time in years since the introduction of the product. So at the time that it's been on the market for 4 years, they would expect that next year they would sell 933 more of it, whatever it is. So it's not that next year they'll sell 933. You'd find that out by plugging in 5 to the original function. But if I plug in 4 to the derivative, then that's how many more I expect to make next year. If it had been negative, then I would expect to make fewer because the number that I will make more would have been negative.